We continue with the explanation of second law of thermodynamics in this video. In the previous video, we discussed the heat engine, and also we derived or we explained the efficiency of a heat engine. If you hadn't get a chance to see that video, please see it here. We discussed the heat engine and the efficiency of a heat engine here. So here we continue with the second law of TD. So it is just to refresh your memory, I'm explaining what I said in the previous video once again. And here is a bit more explanation into the functioning of a heat engine. As you can see here, you've got a heat source, and you supply a certain amount of heat energy here. You got the working fluid, say for example water. You heat the water, generate steam, and the steam pass through here and reaches the turbine. Your turbine blades will be here, and the blades rotate, and you generate work. Let's call it turbine work. And after producing or after releasing the energy, the steam will be condensed here, where it rejects some heat to the atmosphere or the reservoir or a heat sink, some heat, and then it becomes water. The water is getting pumped back to the boiler or wherever you supply the heat, and the cycle thus completes. So you can see here, from a heat source or a thermal energy reservoir, we call this a thermal energy reservoir. We have mechanical energy reservoirs and thermal energy reservoirs. Obviously, the thermal energy reservoir is a reservoir where you can take heat or reject heat, and the quantity that you can take is infinity. That's why it's called a reservoir. So you have a thermal energy reservoir here, which is at a temperature T1. Say for example, and here we can say it's 1000 degrees C, and you take some heat from that reservoir. Say for example, it's 200 watt, or I'm just saying an example here. So, or 200 joule per second heat you receive from the high temperature reservoir. And that's what's happening here. You provide a heat to your boiler, and your working fluid is operating in a cycle here. So you generate that fluid into steam or whatever, or a high temperature or a high energy condition, and that's been given to the turbine. So you produce net work here. So you get not net work, you get the turbine work here. And at the same time, in the cycle, you need to provide a pump work here, because you need to pump the water back to the boiler. So there is a work input here. Let's call this the pump work, and that's what's shown here. So that is a power input into the system. And also you have a heat rejection to the low temperature reservoir. Let's call it another thermal energy reservoir, which is at a low temperature. So obviously from this case you can see temperature T1 is greater than T2, because it is receiving a higher heat, and the heat rejection is low. And as you know, heat can only flow to flow from a high temperature to a low temperature. So this should always be less than T1. So the temperature at the low energy or low temperature reservoir is lower than the temperature at the high temperature thermal energy reservoir. Now that is a heat engine, and the heat engine is most commonly used to produce a continuous amount of work. And we mentioned in the previous video that the net work in a heat engine cycle will be the turbine work minus the pump work, and the heat input is Q1 into the system. Now I mentioned in the previous video that first law only states or it only says the if there is an energy balance as per first law, any process can happen. It doesn't mention anything about whether heat can flow from a low temperature to a high temperature, or whether energy can flow from a low potential to a high potential. It doesn't state anything like that, and that's where the second law is very important. So let's see what happened. Let's evaluate a couple of conditions where we can identify whether the process is possible or not. And I would like to invite your attention to these three conditions mentioned here, where these are all cyclic processes where you either get net work or you get some heat addition into a system or something like that. So let's see each of this. As you can see in the first figure here, you can have you can see a thermal energy reservoir here, which is at T1, and heat Q1 is taken into the system. Okay, that's fine. And we can also state there is a pump work that's been missed from the system. So this is a complete system, but you can see a difference, slight difference here, that in the previous figure it was Q2 to T2, and I stated that T2 is always less than T1. But in this figure what is shown is Q1 from T1, and Q1 again is rejected to T1. Before going any further, I would like to say that all these processes shown in here are impossible. These are not going to happen. This is impossibilities. But that's where the possibility of a process is explained in the second law of thermodynamics. So in this figure you can see a particular amount Q1 of heat is taken from a reservoir at T1, and the same amount is rejected to T1, and you get a network. So yeah, you're right, you actually don't need this this here. Actually you can because I shown that network there, you don't really have to have that work. This is network, so that's fine. You don't, because network, as you know, it is WT minus WP. So you have that that input there. I just didn't realize this is network. So anyway, so this is same temperature at both reservoirs and same heat taken and rejected. So that is not going to happen. That's not possible. If you have to produce a network, you should have a high temperature reservoir and a low temperature reservoir, and you should also have a high rate of heat transfer and a low rate of heat transfer. Then only you can produce a network in a cyclic process. So this is a cyclic process. You have boiler, a condenser, and a pump here. That's one case. Let's see the second figure here, where you have a high temperature reservoir and network and a heat input to the system, but as you can see, there is no heat rejection in here. There is a cycle here, but there is no heat rejection. So in that case, you will get the entire heat input as your network, because you don't lose anything here. If you remember, in the previous video I derived that WT minus WP is equal to Q2 minus Q1 in an ideal case. So if you have no heat, Q1 minus Q2, sorry, it's Q1 minus Q2. So if you have no heat rejection, then WT minus WP, or your network, is equal to Q1, and that's what's shown here. Again, this also is not possible. You should always have a heat rejection to a low temperature reservoir in order to produce network. So this system also is impossible. Now moving on to the third one here, as you can see, this is a, let's say this is let me just clarify this. The assumption here is T1 greater than T2. So if T1, the thermal energy reservoir, is at a high temperature than the thermal energy reservoir here, which means temperature T1 is greater than T2, and you have a heat flowing from T2 to the engine and then a heat from engine to the T1 condition, T1 temperature. But as you can see here, there is no effect other than the flow of heat from a low temperature reservoir to a high temperature reservoir. There is no effect, there is no work input, neither there is no work output. Again, this also is impossible. So it is possible. You can always, it's not a spontaneous process. As I mentioned in the previous video, all spontaneous processes happen in only one direction, from the high potential to the low potential. But in here, heat flow from a low temperature condition to a high temperature condition without any work, that is not possible. It is possible for heat to flow from a low temperature to a high temperature, provided you give some work input. We know we know air conditioning and refrigerators are doing the same thing. They take heat from a low temperature condition and reject it to a high temperature condition, but we give power input for that system to operate. But as you can see here, there is no input power in the system. So at that conditions, this is also not possible. Now let's see what are the statements of second law of thermodynamics. The second law of thermodynamics is formulated by two statements. One, the Kelvin-Planck statement of second law, and second, the Clausius statement of second law. I have already discussed both these statements through the three figures we just saw, but let me explain that once again. Kelvin-Planck's statement says it is impossible for a heat engine to produce net work in a cycle if it exchanges heat with bodies at single fixed temperature. And that's exactly what we say in here. If this heat engine is exchanging heat with bodies at the same temperature, T1 and T1, then it is impossible to produce net work. So in this case, the engine is reacting or functioning between same temperature differences, not differences, same temperatures. So in that case, it is not possible for this engine to produce net work. And that's what the first statement of the second law of thermodynamics. Once again, it is impossible for a heat engine to produce net work in a cycle if it exchanges heat with bodies at single fixed temperature. Now, second statement, that's a Clausius statement of second law. It is impossible to construct a device operating in a cycle that will produce no effect other than the transfer of heat from low to high temperature. Again, that's what we have seen here just now. That is, we have a system here, a cycle here, and what Clausius statement says is, if you want to transfer heat from a low temperature body to a high temperature body, then you have to provide some effect other than the heat transfer, which obviously is a work input. You need to provide a work in for this to happen. If you don't give work input, then heat cannot flow from a low temperature body to a high temperature body, or a low temperature reservoir to a high temperature reservoir. And that is what the second statement of second law of thermodynamics. Once again, it's impossible to construct a device operating in a cycle that will produce no effect other than the transfer of heat from low to a high temperature reservoir. Now there are lots and lots of application of the combined first and second law of thermodynamics, and we will see some of them. I will try to go through most of them in the oncoming videos.